All right. Hi, everyone. Welcome to lecture 24. So in this lecture, we're going to introduce the integral at long last, and then we'll have, both of our sort of main concepts from calculus finally defined. And so the integral, it's sort of harder to define just in the sense that it's more complicated. And there's a lot of notation, which is a little bit irritating. But I think conceptually, if anything, it might actually be easier to understand than the derivative. But whatever the case may be, like I said, it is kind of complicated notationally. So this video, we're going to introduce one concept of the integral. So the most famous, notion of the integral is the Riemann integral, and those are, the Riemann integral is defined sort of as like the limit of what we call Riemann sums. And you might have heard the term Riemann sums before. I've probably said Riemann sums at least a couple times. That's the most common term. But it turns out that that's not really the most elegant formulation, at least of this type of integral. So we're going to first define what they call the Darboux integral. And that's going to turn out to be equivalent to the Riemann integral. So I'll talk a little bit about the Riemann integral at the end. But for now, we're going to focus on the Darboux integral. And so this lecture, or this video here, it's going to be mostly devoted to just defining it, basically. So introducing the necessary notation and then defining the integral. I will, throughout this lecture, as much as possible, try to draw like diagrams to represent everything that's going on in all of the arguments and everything. And in some cases, I might more or less use a diagram as like kind of a substitute for a proof. So in those cases, I definitely recommend that you reference the proof that's given in the book and sort of like try to tie them together. So try to tie the diagrams that you see and like the ideas that I'm explaining to what is actually described in the book in sort of rigorous detail. All right, anyway, so without further ado, let's get into definition 32.1. So, so the idea is we're going to do something very similar to Riemann sums. And so if you remember, so Riemann sums, it's kind of, the idea is kind of like, you have a function and you have some interval that you're trying to like integrate it over. So you kind of divide the interval up into a bunch of little subintervals, and then each one of those has like a rectangle. And then, you might have seen like, a left or a right endpoint version of it or something like that, right? So you create these rectangles, and you do that by kind of like either picking a value of f. Yeah, basically, usually by picking a value of f somewhere in the little subinterval. Like the height of the rectangle is determined by some value of f in that rectangle. So what we're going to do is like, we're kind of going to do something like that, but we're going to be looking at the extremes of like, what's like the biggest possible estimate, given some like subdivision of the interval like this, right? Where you've like chopped it up into small pieces. What is the biggest like reasonable estimate of the area for that subdivision, and what's the smallest reasonable estimate, right? So basically the heights of the rectangles are going to be like the supremum or the infimum of the values of f on the small subinterval you're looking at. So that's why we're going to define at the very beginning here, we say, so let f be a function on AB and S a subset of AB. We write, and this is really, it's just for convenience basically, because we're going to have to write a lot of this. We're going to have to write this a lot of times. So capital M of Fs is basically the maximum, quote unquote, although it's not really the maximum because the maximum might not be achieved, but it's the supremum of the values of f of x for x and s. Notice that with our other notation, remember, you can also write this as the supremum of f of s, right? And then little m of f and s is basically the infimum of f of s, right? So that's the notation just for the sort of highest and lowest values, quote unquote, on a given set. And then of course we're going to be applying this to smaller intervals, right? So so now the thing is we need a way to talk about like subdividing this interval up. And before you've probably seen, you know, like something where you take like a plus k times like b minus a over n or something like that, right? Where you divide it up into equal length subintervals. But for our definition, since we're analysts now, we don't want to restrict ourselves. That's kind of an artificial choice that we don't want to make. So we're actually going to talk about sort of generic ways of like subdividing the interval. So it's possible that you know, our subdivision could be like very uneven for whatever reason. You know, maybe you have a thin rectangle, some thick ones, you know, and so on. So maybe this is A and this is B, and we subdivided it in this weird way for some reason. So ways of subdividing the interval are going to be what we call partitions. So a partition of AB is any finite ordered subset P having the form P equals, so we call A T0, and then there's going to be, you know, T1 up to Tn, which is going to be B. Okay, so basically T0, T1, T2, and so on up to Tn, those are like the points that we pick in the interval to be like the endpoints of various rectangles. And by convention, we always call A, the left endpoint of the interval, we always call that T0. And then if there are n rectangles, we call B Tn, okay? And we always label the points in the interval that are the endpoints of the different, you know, sort of like marking where the different rectangles, you know, begin and end. We always label those in order. So it's like T1 is the right endpoint of the very first rectangle. T2 is the right endpoint of the second rectangle. And it's also the left endpoint of the third rectangle, right? And so on. So given a partition, you can always sort of talk about like Tj is like the, you know, the right endpoint of the jth rectangle or the left endpoint of the j plus first rectangle if you want. Yeah, so that's a partition. And you can partition an interval, right? You can partition an interval in who knows how many, I mean, like in infinite number of ways, right? Because you can choose whatever, you know, really uneven spacings that you want. So given a partition, so given a partition P, the upper Darboux sum, which we write as U of F and P, is defined by U of Fp equals the sum from k equals 1 to n of the sort of upper value of f on the interval tk minus 1 tk times tk minus 1, right? So this is sort of like the height of the rectangle, quote unquote, and this is the width of the rectangle, right? So this is like an overestimate of the area under the graph, and then and the lower Darboux sum L of FP is L of FP. As you can imagine, it's the same thing, but now with capital M replaced by little m. Right. So those are the upper and lower Darboux sums, and so note that so for any partition, UFP is less than or equal to the sum. Oh yeah, hold on. There was a hypothesis I missed. I'll get to that in a sec. So this is less than or equal to the sum from k equals 1 to n of m of f on AB times tk minus 1, which just equals m f AB times times b minus a. And similarly, LFP is less than or equal to the sum from k equals 1 to n of little m, or sorry, not less than or equal to, greater than or equal to, of f AB. So yeah, tk minus 1, which is little m f, AB times b minus a. And in general, L of FP is less than or equal to U of FP for any P. So, so basically, right, all the upper and lower sums are bounded, right? Okay, so one thing I didn't, I think I forgot to mention, f should be a bounded function, okay? So notice that we're not assuming that f is continuous. Hold on. So we're not assuming f is continuous. So it's actually possible, if you just have a random function on AB, it definitely could be unbounded, right? The boundedness, we only know the no boundedness in the case of like continuity, unless we just assume that it's bounded. So we have to assume it's bounded in order for these to even necessarily exist. I mean, otherwise they might just be like infinities. But as long as we assume it's bounded, then all of these numbers are perfectly well defined, including the total maximum and minimum value, or sort of the total supremum and infimum of f on the entire interval AB, right? And so here, all this is literally, it's like every rectangle here, every single rectangle has the same height, right? Which is just this like capital M of f on the entire interval AB. so like you could factor this out of the sum, and then you just get like what's left over is just the length of the interval, right? So that's why it's like capital M times B minus A. And then the same thing happens here, where this is like just you use the same height for every rectangle. It's the smallest value, or like the inf of f on AB, and you can just factor that out again, and you'd get B minus A. So basically, we're just saying that like all of the sums lie between these two like totally extreme values. So in particular, the upper sums are bounded below, right? And the lower sums are bounded above. Like the upper sums are bounded below by this number, and the lower sums, sorry, the lower sums are bounded above by this number, because for any partition, the corresponding lower sum is at least, or is at most as big as the corresponding upper sum. So because that's true, it's possible for us to define. So we can define U of f to be the infimum of every possible upper sum, where P is a partition of A, B, and L of f is the supremum of L of f P, where P is a partition of A, B, right? Because this set is bounded below, right, by the little m of f A, B times B minus A. And this is bounded above by capital M F B times B minus A, right? So these numbers do exist. If U of f equals L of f, we say f is integrable on AB, and write the integral from A to B of f, which is, sometimes we also write this as the integral of A to B f of x dx. I have some feelings about this, but we use this symbol to represent the common value of L of f and U of f, okay? So this you can kind of think of as like the smallest overestimate, right? In a weak sense, right? And this is like the biggest underestimate, right? That's kind of the idea. So it's like if you can, you know, if by making the partition really, really fine, you can get the overestimate and the underestimate to be really close to each other, then the integral exists, right? And it's just whatever value they tend towards. If you can't, right, then there's some kind of a gap between them, and so there isn't really like a well-defined value of the integral, because you don't know whether to choose like the overestimate, quote unquote, or the underestimate, quote unquote, like, because there's no value in between that they commonly like tend towards, right? So one thing I will say is like I greatly prefer this notation to the other one, which is more common in lower, like sort of lower division calculus and stuff like that, because this really emphasizes, right? I mean, this notation emphasizes exactly the data that are involved in defining an integral, basically, right? It's just a function and an interval. So like this x, the x in f of x, integral of f of x dx or whatever, that's just like sort of a notational convenience that lets us do, manipulations and stuff inside of the integral, and it helps us compute stuff. So this notation can be good for computing, But philosophically, I really think that the notation without the x dx component, right, is far superior, and I'm gonna try to stick to that as much as possible, because I think it really it will help you think more clearly about exactly what an integral actually represents. To be honest, I think it really helps. So yeah, this is the notation for the integral, and this is the value, and this is what we call the Darboux integral. The way we've defined it here, that's the Darboux integral. So let's see. Is that, I think that's all for this video. So oh, well, yeah, let me just draw a diagram to help you visualize the definitions here. All right, so here you can just see an example of, some upper and lower sums for some random partition for this kind of a random function. So you can see the points t, A is, of course, that's t0, and then B would be t6. So there are 6 rectangles, right? And for the upper sums, we're always using the supremum value. So I just, for one of the rectangles, I just kind of like marked out, what those values are for the upper and lower versions. So for the second rectangle, you can see, capital M is up here, while little m is down here. Capital M, you can see it kind of, in this case, it appears to have to actually be achieved in between T1 and T2, right? So it's not always at some endpoint. Yeah, over here, for example, in the 6th rectangle, little m is also achieved somewhere between T5 and T6. So yeah, you can also see visually why, for a common partition, right? When you fix one single partition, the upper and the lower sum has to be less than or equal to the upper sum for that specific partition, like for that common partition, okay? If you have two random different partitions, it turns out that the upper sum is still bigger than the lower sum, but it's harder to see why. So that's going to be one of the things we talk about in a few videos from now. But anyway, yeah, I just wanted to give a graphical representation of what these upper and lower sums look like. So I hope this helps. And it'll be good for you to try to visualize something kind of similar to this for as much of the stuff about integrals that we talk about as you can. All right, so in the next video, we'll talk about, we'll look at some examples of proving that functions are integrable or not integrable directly from this definition.